the limit as x approaches 0 of x squared divided by 1 minus the cosine of x. The first thing we have to do is we have to check to see whether L'Hopital's rule applies. Remember here, we have to have both limits be 0 or both limits be infinity. I'm going to stop saying plus or minus infinity because it gets old, but let's say it's implied every time I say it now. So when we check it, we check by direct substitution. Putting 0 in the numerator, x squared, gives me a 0. Putting 0 in the denominator, cosine of 0 is 1. I have 1 minus 1 in the denominator. This is 0 over 0, and so we do have an indeterminate form. Therefore, we do apply L'Hopital's rule. Again, with the h over the equal sign, we have the limit as x approaches 0 of 2x in the numerator and the sine of x in the denominator. After I've applied L'Hopital's rule, the way I compute the limit is direct substitution, as I would have done in a previous chapter. And here, the direct substitution actually yields, in this case, 0 over 0, because I have 2x over the sine of x. We again need to use L'Hopital's rule, and at subsequent steps here, by trying to directly substitute, I'm actually applying the test to see do I use L'Hopital's rule. And the thing is, we just keep using L'Hopital's rule until we don't need to anymore. And so this the limit of as x approaches 0 of 2x over the sine of x, by applying L'Hopital's rule, is the limit as x approaches 0 of x divided by the cosine of x. No, it's not. It's 2 divided by the cosine of x. Excuse me there. Well, using direct substitution, 0 in place of x for the cosine gives me 2 over 1, or just 2. And we're done. Next, let's look at the limit as theta approaches pi of 1 plus the cosine of theta divided by 1 minus the cosine of theta. First, let's go ahead and check, do we need to use L'Hopital's rule? Substituting pi in the numerator, we get 1 minus 1, so 0. That's promising. And substituting pi in place of theta in the denominator, we get 1 minus negative 1, and so 2. Folks, this answer here is 0. This is not an indeterminate form. We're done. L'Hopital's rule did not apply. What if we had used L'Hopital's rule? Like, can we just use it anyway, anytime? Well, the answer is no, and I'll show you what it looks like. Starting with the limit as theta approaches pi of 1 plus the cosine of theta over 1 minus the cosine of theta, if I apply L'Hopital's rule, then I have the limit as theta approaches pi of the negative sine of theta divided by the sine of theta. Dividing will give me actually a negative 1. And so while the true limit is 0, this incorrect application of L'Hopital's rule yields a limit of negative 1. Therefore, we can see they don't match. And we go back to the statement of L'Hopital's rule. If both functions have a limit of 0 or infinity, then I can apply L'Hopital's rule. Next, we'll do the limit as x approaches infinity of the natural log of the square root of x divided by x squared. And realized that I was still writing in blue. Putting infinity in place of x in the numerator will yield infinity, and in the denominator also infinity, and so L'Hopital's rule applies. So this is going to become, using L'Hopital's rule, the limit as x approaches infinity. Well, you know what? Before I apply L'Hopital's rule, so I don't have an h yet. The square root of x is the same as x to the 1/2. So it follows that the natural log of the square root of x is 1/2 times the natural log of x. So in the numerator here, I'm going to write that down, 1/2 times the natural log of x divided by x squared. Now I will apply L'Hopital's rule, and folks, notice what I've done. I've made it so that it is easier to differentiate the logarithmic function. I highly recommend we use properties of logs whenever possible to simplify derivatives. We'll get the same answer either way, but why use the chain rule when I can simply use the property of logs that deals with exponents? So using L'Hopital's rule, we get the limit as x approaches infinity of 1/2 times 1 over x in the numerator divided by 2x in the denominator. This just simplifies as the limit as x approaches infinity of 1 over 4x squared. Substituting infinity in place of x in our denominator now yields 0, and that's our answer. For our next example, we're going to see the limit as x approaches 0 of the hyperbolic sine of x minus x divided by x cubed. I'd like for you to pause the video here and apply L'Hopital's rule and come up with an answer. Come back when you're done. Well, the first thing I want to remind us is that the hyperbolic sine of x is equal to e to the x minus e to the negative x over 2, and so the hyperbolic sine of 0 turns out to be 0. Therefore, our initial check tells us that we do have an indeterminate form for the original limit, and which is 0 over 0. So applying L'Hopital's rule, we differentiate the hyperbolic sine of x. We get the hyperbolic cosine of x minus 1 divided by 3x squared. Checking to see if we're done, we apply the definition of the hyperbolic cosine of x, which is e to the x plus e to the negative x over 2. So the hyperbolic cosine of 0 is equal to 1. Therefore, we do still have an indeterminate form of 0 over 0. Applying L'Hopital's rule one more time, hyperbolic cosine of x minus 1 differentiates to the hyperbolic sine of x. The denominator, 3x squared, becomes 6x when we differentiate. Again, checking to see if we're done, we see that we still have an indeterminate form of 0 over 0. One more time, folks. The derivatives are hyperbolic cosine of x for the numerator, 6 for the denominator. Substituting x equals 0 gives us finally 1/6, which is our answer. We apply L'Hopital's rule as many times as we need to until we can substitute and not have an indeterminate form. And I once again request, every time you apply L'Hopital's rule, please put a little h over your equal sign.